So this is a video in a series where I am going to discuss the concurrency of three lines. It's a series of videos that I'm going to talk about the high school project that I did when I back in my high school days in 2012. And so here is one of the topics that I would like to talk about. It's about the concurrency of three lines, and it is a special case in which the three lines are given in parametric form and in the complex plane. So if I have a complex plane here and we have three lines, gamma 1, gamma 2, and gamma 3, and the three lines are given in parametric form, so gamma 1t is given by alpha 1 plus beta 1t, gamma 2t by alpha 2 plus beta 2t, gamma 3t alpha 3 plus beta 3t, where alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 are complex numbers. So alpha 1 is the starting point of gamma 1 and beta 1 is the direction, and so on. So we are asking the question whether gamma 1t, gamma 2t, and gamma 3t are concurrent. This means we have to find a necessary and sufficient condition for their concurrency. So in order to answer this question, you can think about it, you can pause it and think about it, but here are some hints. So you can consider the Cartesian analog, where if I'm given three lines in the Cartesian form in the plane, xy plane, then say a1 x plus b1 y equals c1 and so on, then the three lines are concurrent precisely when the determinant a1 b1 c1 a2 b2 c2 a3 b2 b3 c3, this determinant equals 0. So it's easy to check the concurrency of three lines if I have them in Cartesian form. And if I want to do this in the complex plane, then it's similar. I just do the Cartesian form analog. So I have u1 bar z plus u1 z bar equals double 1. So if you notice, then the left hand side is in fact a dot product. It's a dot product two times, in fact, two times dot product between u1 and z. And then double 1 is a rational number or real number, because the dot product is usually rational or real. Then and so on. Then these equations are the lines are given by these equations. Then we have a similar concurrency condition where I should have written here u1 bar instead of v1. And this is u2 bar, and this is u3 bar, and then this would become 0 if these three lines are concurrent. If I want to use these results, I can in fact convert the parametric form of the equations to Cartesian form, but this is very tedious. So I'm going to bring a new concept called Apollonius polar duality, where I am making something different. I'm considering the concurrency of lines is converted into the collinearity of points. So in order to do that, I have to make one point correspond to a line. So here is a line, here's a line, and then here is a point. So they are corresponding to each other, and this is called a polar, and this is called a pole. So I want to make each line has a pole and each point has a polar. And how do I define the pole or polar? Well, if I have a line, then its pole is given by this. It's given by it's called set perp. And first of all, I mean a point set. Then if I want to know the polar of this point, then this line is defined as such. I have a line such that this line is perpendicular to OZ, where O is the origin. It's perpendicular to OZ. And then OZ is also parallel to OP, where OP is the meet of the line set perp and OZ. And then P equals K set with K positive. Strictly more than 0. And then we also have the relation in usual inversive geometry, where I have p, this p taken its modulus squared times the set taken its modulus squared equals 1. Where in rational trigonometry we call this cogents. The modulus squared of a complex number is called cogents. So the cogents of p times the cogents of z equals 1. Or you can take the modulus, but cogents is much better in especially rational trigonometry, if I want to do something rational. So I have this equation, p equals kz. If I want to take the cogents, take the cogents of both sides, then I have p cogents equals k squared. I'm sorry, I have a k squared here. K squared times the modulus the cogents of z, and then I can substitute this into this equation. So I have k squared times the cogents of z squared equals 1. So k squared equals 1 over the cogents of z squared, which means k either equals k 1 over cogents of z or minus 1 over cogents of z. But k is positive, so k equals 1 over z squared. I mean cogents of z, which is greater than 0. So this is the polar duality of a complex number. And if I have a line, so I want to find out what the pole of a line is, and this is the theorem of my project says that this is the answer to the question. Is gamma, if a gamma t is the parametric form of a line, then gamma prime t, which is the direction over this is called the cross products between the gamma of 0, which is the start or the starting point, and the direction gamma prime t, where gamma this cross product is complex, is 1/2 a bar b minus a b bar, or for any complex numbers a and b. So as I said, the dual of a line of a point. So this is a proof. The point dual of a point, which is the pole of the polar of the line of a point set. Well, just now we said that p is, first of all, p is on the line. P is on the line. So I can take p, which is equal to k set. Well, what is k set? K is 1 over cogents of z. So p equals z over cogents of z plus something times t. So what is the directions? But we know that z bar is perpendicular to OZ. Z perp is perpendicular to OZ. So if I want to find a perpendicular direction to z, then I multiply z by I. So then this can parameterize the polar of the point z, which is 1 over z bar plus I times z times t. So if a line, I'm given a line gamma t, I want its pole to be z, then we note that by definition, the segment joining the origin and z, which is OZ, is perpendicular to the line gamma. So this is the line, and then I want to find a pole. So we know that this OZ intersects this gamma of t in the point W, say, and z equals kW. Which means that I times W equals some real number times the direction of gamma, and W is gamma 0 plus S times the direction of gamma, because that gamma t can be parameterized by this form. So the start is what this means is that I rewrite this as I'm given the direction and the starting point, which is gamma 0, which is somewhere else, and also the direction is gamma prime t. So W is on the line, so it is given by this, and I times W is equal to is parallel to the direction of that means direction of gamma. So that's the first equation. So I want to solve these two equations. So by rearranging that, put the I of the IW on the right hand side. I have minus I, so I have W equals minus I R times gamma, the direction of gamma prime of t, and then I can substitute the first equation into the second, and then I have gamma 0 plus S plus IR gamma prime t equals 0. So I have to rearrange that, and then by rearranging that, I can consider the I can put the gamma 0 onto one side. I have minus gamma 0, and I can consider the real part and the imaginary part. So this is a real part, and this is imaginary part. And if I have a system of two equations, then I want to solve for S and R. So how to find R? I can use Cramer rule, the Cramer's rule. I first substitute this in this column into the first column. Second, because I want to find R. So into the second column, and then I have a determinant divided by the determinant of these four coefficients. So the first thing I would have gamma prime of t times gamma 0, imaginary part of gamma 0, plus gamma real part of gamma 0 times gamma prime t with a minus sign in front. So this is in fact, if you think about it, this is in fact the cross product. You can think about it yourself. Now I've listed this as an exercise. They have a cross product because basically and then for the denominator, I have real part times real part plus imaginary part plus times imaginary part. Then this is just the quadrants of gamma prime t, but this I comes from the numerator because this cross product is in fact strictly imaginary. So it's something times I. So I will divide it by I to have that determinant. And simplifying gives this. I can cancel the minus and the 1 over I with an I. And then because 1 over I is minus I, and minus I times minus 1 is I. So hence W is minus I times R times gamma prime t. And we can substitute this for R, and then this I multiplying this minus I equals 1. So I'm left with this cross product divided by the quadrants. But then this quadrants cancels with this gamma prime of t itself to give this gamma prime t bar. So W, this is what W is. So I'm going to find Z. So I want to find, so as I said, the Z equals K times W. So I have to multiply this, I have to find this K. But we know that the quadrants of Z times the quadrants of W is equal to 1, or the modulus, if you like, the moduli multiply to 1. So the modulus of W times the modulus of W times K in absolute value is equal to 1, because I can substitute Z equals KW into this. And then K is equal to 1 over the quadrants of W. So Z is equal to 1 over quadrants of W times square W times W, which is 1 over W bar, and this is this is W. I think I missed out something, in fact. So how do I find 1 over W bar? Well, I know that W inverse is in fact W bar over the quotient, right? If I consider 1 over W bar, then this is equal to W over the quotients of W. And I know that the quotients of W, well, what is the quotients of W? The quotients of W is this number, is R squared times the gamma prime T, the quotients of gamma prime T. Okay, so what is R squared? This is R squared. This is R, I mean. And R squared is, this is becomes minus 1, this squared, and then this goes to the 4th power, and then this gamma prime T, well, then this quotient cancel with this quotient, and then I'm left with gamma prime T squared, and then this thing would become squared. That is what okay, or another this is a that is the very that is not the correct way to do that. I can have 1 over W is to change the numerator and denominator, and then 1 over W bar is take the conjugate of both numerator and denominator. So I have gamma prime T over minus this thing. Why minus? I don't know. Yes, I know. Because this is strictly imaginary, so it's a complex number, and it's something times I, some real number times I. So its conjugate is minus that number. Okay, so then the thing is that how is this connected to the concurrency of 3 lines? Some problem. The reason is because well, if I have 3 points, set 1 and set 2 and set 3, then they're concurrent. They're collinear. I mean, the 3 points lies on the same line precisely when this determinant is equal to 0. And then we know that the pole. So if I have 3 lines passing through the same point, this means that their pole will be collinear. So this is, say this is L1, L2, and L3. Then perhaps this is L3, I think, perhaps L1, perhaps, and L2, perhaps. This is the magic about polar duality. If I have two lines passing through the same point, then then these 2 points lie on this line. But then if this point also pass through the same point, then this dual will pass through the. So what does it mean? If I have this point lies on the L1 perp, so say this is A, and say this is A perp. So if L1 passes through A, then A perp passes through L1 perp. So A perp passes through L1 perp. And the same holds for L2 and L3. So if the 3 lines are concurrent at A, then A perp will go through the perp of these 3 lines. So these 3 points are in fact collinear. This is the magic about polar duality. So if I want to find out necessary and sufficient condition for the concurrence of the three lines, then basically I want to find the collinearity of their poles. So if I given the 3 point lines, then they are concurrent precisely when their poles, which can be given by the similar formula as this if we number the gammas. And using the determinant equation here, then the 3 points, then the determinant will be equal to 0. So here's the proof. The lines are concurrent precisely when the duals are collinear. So I apply this pole formula into these 3 points. This is the poles of the 3 lines, the collinear. So this holds precisely when I substitute this into the first row, and then they conjugate into the second row. I zoom in. So I think there is a bar here that is missing. And then we type poles here. And then I multiply the 2 sides by the denominators. And then, well, how to do that? Well, first multiply the first column by the denominator. So I have the first number becomes this. And then, with a minus sign, in fact, with a minus sign here. And then the second column is so on, and the third column and so on. And then I multiply both sides by minus 1, then I would have this very nice determinant with equals 0, where if all of this, well, there is some problem with the pole, of course. If the denominator is 0, then there will be some problem. I will talk about it later. So what about then these 3? I can take the normal factor, if you like, unit factor, the unit direction out, and then this I can multiply this by this. If you like, then I would change these factors into normal unit factors. But that step is not necessary, in fact. Okay, so why? Then we have to consider this thing, because this appears in the denominator of the pole formula. So we have to know how we are going to deal with this. If a dual of a line is given by this formula, there is a problem. If the gamma 0 and gamma prime t are parallel. Why? Because if these 2 complex numbers are parallel, then their cross product will be equal to 0. But what does that mean? That means that if the sub and the direction is parallel, so if a complex number, say w, is parallel to the direction of the line, so then the line will pass through w, and it will also pass through the origin. That is exactly when the pole of this line is the line at infinity. The line is passing through the infinity. So how are we going to deal with this? Well, we have to consider something in the projective manner. So does this condition still hold? Well, at that time I have no time to consider this, so I dismiss that as a side note. In that case, I have to do something different. I would have this parametric equation would, in fact, what I thought that at that time would in fact be nonsense. In fact, so I may want to leave that to the readers or the viewers to consider. What happens if the denominator of this formula equals 0? Well, you can comment on that, and in fact I may want to do another video after thinking about it more. Maybe next time I'll talk about that, or maybe not. If you can think of, you have any ideas, and maybe you can comment there, and then I may take that and consider from that point on and do something else. So thanks for watching. Thank you.